Hello, and now we have to find the center of mass of the two-dimensional of the planar body, is also known as lamina. Let us first take an example. The lamina is in the form of sector of a circle which is subtending an angle, suppose 2 alpha, at the center. This is alpha, this is also alpha. So our procedure remains same. We will take a small element. The mass density of this is assumed to be uniform. Now this is a plane body. This is the origin A, B. We have x-axis, y-axis. So in this position, center of mass will be varying only about x-axis. So let us take a small element here. This whole area. This is a small element. Now we can take this small element like this also. If I show it separately, this length is r, the radius, and it is subtending an angle theta here, or making an angle theta with x-axis positive direction, and at the center it is subtending an angle d theta. So its area, we can approximate this to be as a right angle triangle, because this straight line and this curve, they have almost same length, very small difference if d theta is very small. So I can write that dA, its area, is half into base into height. What is height? This is approximately r d theta. So half of r square d theta. Mass density is constant. Let this be equal to rho, mass per unit length. So what is the mass of this small element? dA into rho, half r square rho d theta. Now its center of mass of this right angle triangle, approximately, you know that this is lying at a distance of, total is r, so 2r by 3 from this point. So this is the center of mass. So if I drop a perpendicular from this point here on the x-axis, then this angle is theta. This is up to this point, it is 2r by 3. So this distance will be 2r by 3 cos theta. This is x coordinate of center of mass. So the center of mass is given by integral x dm by integral dm. Putting the mass value here, x is 2 by 3 r cos theta into dm, half r square rho d theta by integral of dm, half r square rho d theta. Theta is a variable varying from minus alpha to alpha. R and rho are constant, so they can be taken outside. So this becomes 4 by 3 r square r cube. Here we have r square. So r, rho is cancelled. Integral cos theta d theta by integral d theta. The limits minus alpha to alpha. Or xc is 4r by 3 sin theta minus alpha to alpha divided by theta minus alpha to alpha. 2 sin alpha divided by 2 alpha, or this is 4 sin alpha by 3 alpha. 4r sin alpha divided by 3 alpha. I think here we should have 2r by 3 because this 1 by 2 will be cancelled. So this is 2r by 3, 2r by 3. So finally it is 2r sine alpha divided by 3 alpha. So you can check what is the value for a particular value of 2 alpha, and if you have a lamina of this shape such that this angle is 90 degrees, so 2 alpha is pi by 2. In that case xc is here along this axis 2r sine pi by 4 divided by 3 into pi by 4. So this is 8r divided by 3 root 2 pi. So this way you can solve it. This is a semicircular disc having uniform mass density. The radius of this is r. So it is symmetrical about y-axis. So center of mass will be varying only about y-axis and not about x-axis. So what we do is we divide this into small annular rings. This is one such ring, and we will find the center of mass of this and integrate for all. The radius of the disc is r. So we can find mass per unit area, rho. This is m is the mass of this disc, m by pi r square. This is the mass density. And this small disc, suppose this is having a radius equal to r. If I draw a separate diagram for this, radius is r and its thickness is, breadth is dr. So its area is dA pi r into dr. If you open it, its length is pi r into breadth is dr. So it will open in the form of a rectangle. This is pi r, the circumference, and this is dr. So its mass is rho pi r dr. What is y? Y is the distance of center of mass of this measured from the origin along y-axis, and this is given by 2r by pi, which we have previously proved for a ring. So now putting the values here, yc is 2r by pi into dm. Dm is rho pi r dr divided by integral dm, that is equal to the mass, because mass density is constant. So 2r by pi rho, pi cancels out, rho integral r square dr by m. Integral dm is equal to its mass. So now put the value. Small r, radius is variable from 0 to capital R. So rho is m by pi r square divided by m, integral r square. So this becomes r cube by 3. So yc is, m will be cancelled, 2r divided by 3 pi. And here we have written the area of full circle, so it should be halved, because this is a half semicircular disc. So 2m by pi r square. So if you put the value here of rho, so this becomes pi. This is how you can find the center of mass of a semicircular disc. Now after this, we have a lamina, the profile of which is in the form of a curve like a parabola. You have to find the center of mass of that. This is a lamina, and this profile is in the form of a curve y equal to k x square. This is a parabola. This length is a, this length is b. You have to find the position of center of mass of this. Taking this point as origin, this is the y-axis, and let this be the x-axis. So coordinate of this point are AB. That means AB is lying on this curve, so it will satisfy the equation. So B equal to k a square. This gives k is equal to b by a square. So the equation becomes y is equal to b by a square into x, because k was not known to us. Now the center of mass is varying about both x and y axis. So what we have to do is, this is a lamina, its mass density is assumed to be constant. Is equal to rho. So we have to find its area, mass per unit area, and for that you have to find its area. So this you can do by taking either a vertical strip or a horizontal strip, both. I am taking the vertical strip. You can do this by taking the horizontal strip also. That is a similar procedure. So this is a vertical strip, and its height can be taken as equal to y. Distance from x-axis, origin from the y-axis is x, and this breadth is dx. So first of all you have to find its area. Area of the strip is given by y dx. And xc, the x coordinate of its center of mass is given by x dA by integral dA multiplied by the mass density. So mass density is constant, so rho can be eliminated from or be cancelled out from denominator and numerator both. So this is equal to x dA is y dx by integral y dx. So we can evaluate this by putting the value of y by a square into x square. And x is the variable 0 to a clearly. So b by a square will be cancelled. So this is equal to integral x cube by integral x square 0 to a 0 to a. So this is a4 by 4 divided by a cube by 3. So this gives equal to 3a by 4. So 3a by 4 at a distance of 3a by 4 from this point is the x coordinate of center of mass of this is line. So this is how you can find the x coordinate of this. Now as far as the y coordinate is concerned, this can be approximated as a rectangle. Approximately this can be taken as a rectangle, and this height is y. So center of mass of this is lying at a height of y by 2 from the base. So the y coordinate is y dm by integral of dm. So here I will write in place of y by 2 integral of dm. Now you can put the value here, rho into y dx by integral of rho into y dx, and you can put the value of y. Rho is cancelled, so y square by 2, 1 by 2 y square. Y we will put from here, b square by a4 x to the power 4 dx upon b square by b by a square integral x square dx. X is varying from 0 to a. So you can evaluate this integral. This is very easy to do, and the answer you will be getting as equal to 3b by 10. So the center of mass of this curve can be shown as equal to or lying at a point here. X coordinate is 3a by 4 and y coordinate from this base is 3b divided by 10. This is the center of mass of this lamina. Now let us find the center of mass of a body which has been left after some portion of it has been cut. This is a circle, and from this I am cutting or I am making a hole in it of circular shape, its diameter is equal to the radius of the original circle. This radius is r. So this has been removed. So you have to find the position of center of mass of the remaining body. So we can show it like this. If you see it from the front or the top side, front side, sorry, this is the top view. This is the original disc, and from this much portion has been removed. It means the mass on this side is more. So center of mass initially was here at the center O. Now it will shift to this side. So this is r, the diameter of this hole, and original radius of the disc is also r. So it is symmetrical about x-axis, origin x, y. So center of mass will be varying only about x-axis. No need to calculate y-axis center of mass coordinate. So xc is, we have two bodies here. One is the disc without hole, and two is the disc which has been removed, or the hole which has been removed. That is also a circle. Its center is C. O is the origin, is having coordinates 0, 0, center of mass coordinate of original body, and of the second body the center of mass coordinates are r by 2, 0. So I will write here m1 x1 minus m2 x2, because m2 has been removed out of it, upon m1 minus m2. So what is m1, what is m2? m1 is the mass of the original body. Suppose the mass of this body, or I can write the mass in terms of area. So area into mass density. Mass density is constant for the whole body, rho into pi r square, whereas m2 is rho into pi r by 2 whole square, rho pi r square by 4. So if I write this as equal to m, this will be m by 4. x1 0 and x2 r by 2. This is the positive side. So m1 is m into 0 minus m2 is m by 4 into r by 2 divided by m minus m by 4. So minus, you can put the value of m, rho into pi r square into r by 2 upon 3 by 4 of m. Find the value of this. Rho pi r square will be cancelled. So minus r by 2 into 4 by 3 minus I think this should be r by 6. Let us check it again. So here this should be m by 4 divided by 4. So we get this as equal to minus r by 6. That means the center of mass has shifted on this side at a distance of r by 6. This is the negative side. So you can see that center of mass always lies towards the heavier part of the body. So the shape of this hole can be of any type. It can be a square hole also, it can be a triangular hole. We have taken a circular hole, so you can try for that also. Now this was the case when the body was detached. We can have the case when a planar body is attached to another planar body. So next question, we have an I section. And you have to find the position of center of mass of this having uniform mass density. So it is symmetrical about vertical axis. This is the y-axis, this is the origin, this is the x-axis. Center of mass will be lying or varying only about y-axis. The dimensions are given 5, all dimensions are in centimeter. This is also 5. 30 centimeter, 5 and 5, all are in centimeters. This is 15 centimeter, the web portion. We have to find the center of mass of this. So what can we do? We can divide this into 3 bodies which are attached together. You can divide by any method. So this is the simplest one. 1, 2, 3. So the center of mass is given by y. We have to calculate only y coordinate. m1 y1 plus m2 y2 plus m3 y3 upon m1 plus m2 plus m3. Mass density is mass per unit area. Rho assumed to be constant. Now body 1. Let us write areas A1 equal to, for body 1 it is a rectangle, 30 into 5 centimeter square. A2 is 15 into 5 and A3 is, this dimension, breadth of this is 20 centimeter. into 5. What is y1? For the first body, centroid from the origin. You can select the origin anywhere. It is easier if you take it here because center of mass is varying only about this. So this is our positive direction. So center of mass of a rectangle is at a distance of half of its height. Height is 5, so y1 is 5 by 2. This is y1, 5 by 2 centimeter. Then we have y2. From this point, center of mass of this one, this is lying at a distance of, total is 15, 15 by 2 from this line. So 5 plus 15 by 2. And y3 is for the third body, 5 plus 15 plus 5 by 2. So yc is mass density into area, 30 into 5, 150 into y1, 5 by 2 plus 75 into y2 is 25 by 2 plus third area is 100 into y3 is 20 plus 5 by 2, 45 by 2 divided by total area. So this will give you the value of y coordinate of the center of the mass, and it is lying at around 10.97 centimeter from the base. So this is how you can center of mass of a planar body like this. Similarly, we can find the center of mass of any other type of planar body which is given to us. Remember that for the symmetrical bodies, the center of mass is always lying at the geometrical center. Now next, after this, we will be discussing the center of mass of the solid bodies.